Hello everyone, my name is Ozan Candogan and I am delighted to present my joint work with Philipp Strack on optimal disclosure of information to a privately informed receiver. In this paper, we focus on the problem of an information designer who tries to influence the action of a receiver who has some private information. In particular, in our setting, the payoffs of both the designer and the receiver depend on the underlying state omega, the receiver's private type theta, and her action A. We will allow the action space to be quite general, it's just a compact set, and we will not require the state space to be finite. We will assume that the state belongs to the interval 0 to 1. We will assume that the type belongs to a finite set, which has cardinality n, and this number n, the number of distinct types n, will play a role in some of our results. The state has CDFF and density little f, and type distribution is G. And there's one assumption in the paper that's a little bit stronger than the rest, and it is that the dependence of the receiver's payoff U and the designer's payoff V on the state omega is linear. So these payoffs U and V can be expressed as you see in the slide. Here's the timing of events. The designer first commits to a menu of signals n. Here, each signal mu in the menu assigns to each state omega a conditional distribution over a set of signal realizations S. So when the state realization is omega, we draw a signal from the associated distribution. Here these distributions play an important role because after observing the state signal realization, the receiver is going to update her posterior belief about the state, and these belief updates heavily depend on the distributions from which the signals are drawn. Another important point is that the designer, when she chooses her menu, does not know or observe the state. She knows only the state distribution and the type distribution. Second, receiver picks a signal from this menu. And third, receiver observes the signal realization, updates her posterior belief about the state, and chooses an action to maximize her payoff. Of course, the receiver's choice impacts the designer's payoff. So if in order to maximize her payoff, the designer needs to carefully design her menu. And this is our research question. How should the designer choose a payoff maximizing menu? And are there any structural properties of payoff maximizing menus? Here's a quick summary of our findings. First, we established that it is optimal to use a menu of Luminary Partition signals. In particular, each signal is obtained through a partition of the state space, and all states in a partition element yield the same signal realization. Here's an illustration of a partitional signal. The horizontal bar you see on the slide is meant to represent our state space, and we first obtain a partition of it into 3 partition elements in this example, red, green, and blue. And when the state realization belongs to one of these, we simply reveal that. The signal simply reveals that fact. For instance, if the state belongs to one of these green intervals, the signal realization for our partitional signal is green, and a receiver who observes the signal realization can infer that the state belongs to one of these green intervals, but she doesn't know, for instance, which of these green intervals contains the contains the state realization. There's additional structure of these partitions that define the signals. They, in particular, admit a laminar structure. I will define what this means later on, but this basically will imply that there is a partial order on the partition elements that define these signals, and an implication of this order will be that the convex halves of partition elements are either nested, as in red and green here, or they will not intersect, as in red and blue that you see in this slide. Actually, the signals can have slightly richer structure than what this picture illustrates. At the end of the day, the state space will be divided into subintervals. In some of these subintervals, we will fully reveal the state. In others, we will further partition these subintervals to using laminar partitions to obtain regions like the red, green, and blue that you see here. And we will associate a signal realization with each of these partition elements. So we'll have the pooling intervals and intervals where we fully reveal the state. In each of these pooling intervals, we'll have a laminar structure, and in each of these pooling subintervals, we will have at most n+2 different colors or n+2 different signal realizations. Remember here, n is the number of distinct types of the receiver, and this is how basically says that as you might intuitively expect, when there are more different types of the receiver, in order to satisfy instantly compatible type of constraints, the partition that the optimal signals rely on will have a more intricate, more complicated structure, and our result captures that. I will discuss these two results in some detail in today's talk, but the paper has some other interesting results, so please check them out. One result I would like to highlight is that in settings where the set A is finite, we show that we can actually obtain the optimal menu and these partitions by solving a simple finite dimensional convex program. Secondly, so algorithmically, we have a tractable approach for characterizing these optimal menus. Secondly, there are beautiful papers in the literature which focus on settings where the receiver has binary actions, and they establish that in those settings, public signals that do not require type elicitation are optimal. In our context, these are menus of size 1, effectively. We show that when you go beyond 2 actions, these type of signals are actually quite suboptimal, and we construct examples where such public signals achieve 1 over n of the optimal value that our optimal menus obtain. So there is real value in carefully constructing these menus. And there's a big distinction between the binary action setting and the more general settings where we have more than 2 actions. Let's take a closer look at the designer's problem. Earlier, I mentioned that the designer tries to choose a menu that maximizes her payoff, but it's not clear how to directly obtain this menu, given that a menu consists of a bunch of signals, and it's not clear how to optimize over signals, given that the set of all possible signals is very rich. We'll take a slightly different approach. We are going to formulate the designer's problem as an optimization problem over posterior mean distributions that can be induced by her signals. Here, the key observation is that the receiver and the designer's payoffs both depend on the state linearly. Therefore, posterior mean is the key object that matters when we think about the payoffs that will be induced in the interaction between the receiver and the designer. Specifically, suppose that the receiver observes a signal realization that induces a posterior mean of m. It's easy to figure out which action the receiver will take and the payoff she can obtain when she chooses the best action. And it also is easy to figure out what payoff this action will yield to the designer. These are my indirect utilities U bar and V bar defined in this slide. These capture the payoffs that the receiver and the designer achieve when the posterior mean is m and the receiver picks the best action for herself. Second ingredient of my approach is the posterior mean distributions that can be induced by some signal mutator. It turns out the set of all posterior mean distributions that can be induced by a signal is easy to characterize. This set is pinned down in terms of the MPC or the mean preserving contraction constraints that are given in the second bullet point. Here I need to impose this inequality for every omega in the state space, and it needs to hold with equality at omega equals to 0. Third, the revelation principle applies, and it suffices to restrict attention to menus that contain a single signal for each type, mu theta for type theta, that satisfies an incentive compatibility constraint, which says that type theta has incentive to pick signal mu theta over any other signal in this menu. This incentive compatibility constraint is stated in the third bullet point. It can be expressed in terms of my indirect utilities and the posterior mean g theta associated with type theta's signal mu theta. Collecting everything together, we can express the designer's problem as in the last bullet point. We are optimizing over distributions that satisfy the IC and MPC constraints, and the objective is the expected payoff of the designer, which again can be expressed in terms of the indirect utility V bar and the posterior mean distribution G theta. Now, this still is a non-trivial optimization problem because you're optimizing over distributions. This is an infinite dimensional optimization problem that also has a constraint space that is quite non-trivial. The MPC constraints are imposed for every omega in the state space, which is a continuum. Still, we can obtain some structural properties of the optimal solutions to this problem by conducting a simple thought experiment. Suppose that we started an optimal solution, G star, and we fix some type theta, And for remaining types, we fix the distributions G minus theta star. For type theta, to type theta, we assign a different distribution H, so that the collection of H and G minus theta star still satisfy the MPC and the IC constraints. So when I simply modify the distribution of type theta, I still want to obtain a collection that satisfies the MPC and IC constraints. The constraints that this distribution H need to satisfy are actually easy to characterize. MPC constraint is exactly as before, and the IC constraints can be expressed as in the constraints of the optimization problem that I have in the middle of the slide. Here, the first constraint says that if I assign distribution H to type theta, the payoff she has should be larger than the best payoff she can obtain by not reporting her type truthfully. The latter quantity is a constant because in my total experiment, I fix the distributions of types other than theta, and I can compute what the best payoff of type theta from deviating to one of the other distributions G star theta prime looks like. Similarly, for the remaining types, I need to ensure that they don't have incentive to deviate to type theta's distribution H. This can be expressed as in the last constraint of my optimization problem, where the eta is the payoff that type eta achieves when she reports her payoff truthfully, and if she deviates to distribution H, her payoff should weakly decrease. Now, it's easy to see that our original distribution G star theta solves this optimization problem, where the constraints over H ensure that the MPC and the IC constraints hold, and the objective is the payoff that the designer achieves from type theta, when receiver has type theta. If G theta star is not a solution to this problem, this would imply that by picking the optimal solution here H star and replacing G star theta in the original menu with H star, we would obtain a solution to the original problem of the designer that has a strictly better payoff. This would contradict the optimality of G star. This cannot happen, so it follows that G star solves this optimization problem. But then this tells us something interesting, right? We have a class of optimization problems here where we are optimizing our distributions that satisfy MPC constraints plus n side constraints. Here for each type, I have a associated side constraints. What are the optimals? What are the fundamental question is, what are the optimal solutions of optimization problems of this type? Do they have some special structure? Interestingly, the answer is affirmative, and there is a real neat mathematical structure that the optimal solutions to these problems satisfy. Let me denote by H star the optimal solution. The optimal solution H star satisfies one of the two conditions here. Here Ij are some disjoint intervals, subintervals of the state space. If I focus on states that do not belong to these intervals Ij, then H star should exactly match F, the prior distribution. Within these intervals Ij, H star is a discrete distribution with mass points mkj with probabilities pkj, and the distribution H star is such that to each interval Ij, H star and F assign the same probability, and the expectation conditional on the realization being in Ij is identical under distributions H star and F. One thing that I forgot to mention, which is important, is that this H star distribution has mass points within each of these intervals. It has at most n plus 2 mass points, where n is the number of side constraints that our optimization problem had. How do we establish such a result? Well, we first start with optimal solutions to our optimization problem, where the set on which the MPC constraint binds is maximal. And we show that if the claim of this proposition does not hold, then we can construct an optimal solution where the MPC constraint binds on a larger set, but that contradicts the maximality of the initial solution. Therefore, it follows that the maximal solution that I described satisfies the properties that the proposition states. Here, observe that there are regions where H star matches F, and there are regions where H star is discrete and F is not. In the context of our persuasion problem, the subintervals where H star and F match will correspond to states where we fully reveal the state. and the intervals I sub j will correspond to subintervals where we pool states to different signal realizations to induce a posterior mean distribution as captured by H star. So the question becomes, this is structural property of the optimal distribution H star, but how can we come up with a pooling strategy that induces H star? And this is where the idea of luminary partitions kick in. I'm going to call a partition a luminary partition if for some permutation sigma this condition holds. Here, this sigma is effectively inducing a order on the partition elements. And for this talk, let's assume that sigma is the identity operator. What this laminar condition implies is that the kth partition element is equal to the difference of its convex hull and the convex hulls of all other partition elements that are smaller in my order. This is a mouthful and a condition that's not easy to parse in a talk, but an implication of this condition is easier to parse. It says that convex hulls of partition elements either do not intersect or are nested. I argued in the beginning that the picture on the left satisfies these conditions and is a laminar partition. The one on the right is not. Here the convex hulls are not nested and they do intersect. Why did I introduce this notion? It turns out that for each interval ij that I had in the earlier slide, there exists a laminar partition that induces exactly the posterior mean distribution H star. The proof is inductive, and it also yields a tractable algorithm for obtaining the partition. Putting everything together, we obtained the structure of the optimal menu in our original information design problem. In particular, we established that there exists an optimal menu such that the signal of each type theta is laminar partitional. Basically, for each type, we have a partition of the state space. There may be some regions, like the gray region here in my figure, where we fully reveal the state if the state were to belong to this interval, and there may be other regions like the left and right colorful regions where we do not reveal the state. These are pooling regions. We obtain a laminar partition of these regions and reveal the partition element to which the state belongs to the receiver. And this induces the optimal posterior mean distribution that maximizes the designer's payoff. I'm not discussing it here, but if the action space is finite, one can actually obtain the optimal posterior mean distributions and the partition that you see here by solving a convex program, and there's a tractable approach. Please see the paper for details. I'm going to stop here. The first 4 bullet points are things that I already mentioned. The 5th one is the thing that I would like to highlight. While we were shedding light on the structure of optimal information structures in our information design problem, along the way we derived some general insights on optimization problems with an NPC constraint plus some side constraints. These type of constraints are relevant in many other settings as well. We discussed these in the paper, and I think there's a lot to do in this direction. I hope some of you will find them interesting. Thank you.